Topic: Simple harmonic motion, SHM. This is defined as the periodic motion of a body or particle along a straight line, such that the acceleration of the body is directed toward a fixed point, and the acceleration is proportional to its displacement from that point. Examples of simple harmonic motion. Number 1, motion of a loaded test tube oscillating in a liquid vertically. Number 2, the beating of the heart. Number 3, the motion of a body suspended from a spiral spring. Number 4, the motion of the prongs of a turning fork. Number 5, the motion of the piston of a gasoline engine. Number 6, the motion of the pendulum of a clock. Number 7, the motion of the balance wheel of a watch. Number 8, the motion of the trunks of the musical instrument. Some examples are shown in the figure below. Figure 1.0 shows the pendulum bob suspended by means of a thread. The pendulum swings to and fro. It comes back to its original position. That is one example of simple harmonic motion. Figure 2.0 shows a loaded spiral spring with mass mg suspended on it. Figure 3.0 illustrates loaded test tube swinging in liquid. Simple harmonic motion from circular motion. In the figure above, K, Q, D, S, and R are points on a circle, while T is the center of the circle. A is the radius or the amplitude, and theta is the angle swept through by the radius or the amplitude. X is the displacement from the center, T. In the figure above, A is equal to the radius of the circle. Omega is denoted the angular velocity, while theta is the angle turned through by the radius. Cos theta is equal to x over a. When we cross multiply, x equals a cos theta, and v equals r times omega, where r is equal to the amplitude a. So the speed is given as omega a. The amplitude of a simple harmonic motion A. This is the maximum displacement of the body performing simple harmonic motion from its equilibrium or central position T. The period of a simple harmonic motion T. This is the total time taken by a vibrating body to make one complete revolution or cycle about a reference point. Frequency of a simple harmonic motion F. This is the number of complete revolutions per second made by a vibrating body. Frequency F is equal to 1 over T. When we cross multiply, T will be equal to 1 over F. Summary 01. V equals omega A, where omega is angular velocity and A is amplitude. And F is equal to 1 over T, and T is equal to 1 over F. The linear velocity V is maximum when x is equal to 0. But at D, the angular velocity becomes equals omega A because x is equal to 0. But x is equal to a cos theta, and theta is equal to omega t. Since omega is equal to theta over time, which is angle turned through with time, x equals a cos omega t. When we differentiate, we have that dx over dt equals minus omega a sine omega t. But v equals dx over dt, which is omega a sine wt. The speed of simple harmonic motion v is then given as minus omega a sine omega t, where omega is called the angular velocity and a is called the amplitude equal to the radius. Acceleration of a simple harmonic motion A. Since acceleration is equal to change in velocity over change in time, hence a is equal to dv over dt, but v is equal to minus omega a sine omega t. Dv over dt equals minus omega a times omega times cos omega t. So a equals minus omega squared x. So we can define the acceleration of simple harmonic motion as the product of the square of the angular speed and the displacement x of the particle from the central position. The negative sign indicates that the acceleration is in direct opposite direction with the motion, while the displacement x is measured from that point outwards. Figure 5.0 illustrates the relationship between the angular velocity and the acceleration. There, L stands for the length of the rope or thread, while T denotes the period of oscillation, and the weight is denoted downward, which is mg. So, theta is equal to x over L, but when theta is small, sin theta becomes theta. So, theta equals x over L, but A equals minus omega squared x, equation 1. MA equals minus mg sin theta. When we divide through, theta becomes x over L. So the acceleration A equals minus g over Lx, equation 2. If A is equal to A, then W square x equals A over L. That is, W squared equals G over L. Hence, omega equals root G over L. But F is equal to 1 over T, and T is equal to 1 over F. And omega is equal to 2 pi F. So F equals omega over 2 pi. Since the period is equal to 1 over F, then the period becomes 2 pi over omega, which is 2 pi times 1 over root G over L equals 2 pi root L over G when we divide through. Where L is the length of the pendulum, energy of a simple harmonic motion. The energy transformation in a simple harmonic motion is from potential energy to kinetic energy, and from kinetic energy to potential energy, as shown in figure 6.0. At point A, PE is maximum, that is equal to mgh, while KE is 0 because there is no motion at A. At O, H is equal to 0, and PE is equal to 0, then KE is equal to maximum, which is half mv squared. KE is equal to PE, that is half mv squared equals mgh. When we divide both sides and cross multiply, we have that v squared is equal to 2gh. When we square both sides, we have that v equals root 2gh. So the total energy of a simple harmonic motion E equals half Ka squared, where A is amplitude and K is the force constant of the string. But V squared is equal to K over M root A squared minus Y squared. That is V equals root K over M, open bracket A squared minus Y squared. But V equals omega root A squared minus Y squared. If V is equal to V, then root K over M, open bracket A squared minus Y squared close, equals omega root A squared minus X squared. But Y squared is equal to S squared, since they are displacement from the central position. So omega equals root K over M. But omega is equal to 2 pi F, and T is equal to 1 over F, which is equal to 2 pi over omega. When simplified, the period becomes 2 pi root M over K, where M is the mass of the body and K is the force constant. Summary 0.2. V equals omega root A squared minus X squared, where X is a point from the center. 2. Acceleration is equal to minus the omega squared X. 3. T equals 2 pi over omega. 4. Omega equals 2 pi F. Question 1. A body vibrates in simple harmonic motion with a frequency of 150 Hz and an amplitude of 7 centimeters. Find A, the period, B, the acceleration at the middle and at the end of the path of oscillation, C, the velocity at the middle and at the end of the path of oscillation, D, the velocity and acceleration at a distance of 30 centimeters from the center of oscillation. Solution. Since the period is 1 over F, that is T equals 1 over F, T will be equal to 1 over 150. When simplified, will give us 6.67 times 10 to the power minus 3 seconds. B, acceleration is equal to minus omega squared x. At the midpoint of vibration, that is at x equal to 0, A becomes minus omega squared times 0, which is 0 meter per second squared. At the end part, that is when x is equal to A, the amplitude, which is equal to 7 centimeter, A equals omega squared A. That is, omega is equal to 2 pi f, which is 2 pi times 150, which is 300 pi. Then A equals to 300 pi squared times 7. When simplified, we have 6,300 pi squared meter per second squared. But pi is equal to 3.142, so A equals 6,300 times open bracket 3.142 squared meter per second squared. When simplified, the acceleration becomes 6.2194 times 10 to the power 4 meters per second squared. Ci. V is equal to omega root A squared minus x squared. At x equal to 0, V equals omega A, which is equal to 300 pi times 7 over 100 to convert it to meters. So we have 21 pi meters. That is the speed at the midpoint. Then at the end point, at s equal to the amplitude A, V equals omega root A squared minus A squared, which is equal to 0. Di, velocity at a distance of 3 centimeters. Since V is equal to omega root A squared minus S squared, at S equal to 3 centimeters, V becomes 300 pi root 7 squared minus 3 squared. That is 300 root 49 minus 9 equals 300 root 40. When simplified in short form, we have 6 pi root 10 meter per second. That is velocity at a distance of 3 centimeters. Dii, acceleration at a distance of 3 centimeters. Since A is equal to minus omega squared x, which is equal to 300 pi squared times 3 over 100 to convert it to meters, when we simplify, we have 2,700 pi squared meter per second squared. Summary 3. The period is equal to 2 pi over omega, which is equal to 2 pi root m over k, where m is the mass of the body and k is the force constant or stiffness of the string. Omega is equal to 2 pi f, where omega is equal to angular velocity, f is equal to frequency of vibration. Also, the total energy E of a simple harmonic motion is equal to E equal 1 over 2 Ka squared, where A is amplitude, which is equal to R, and K is the force constant or stiffness of the string. Question 2. A body of mass 30 grams is suspended from the end of a spiral spring whose force constant is 0.8 Newton per meter. The body is set into a simple harmonic motion with an amplitude of 0.6 meter. Calculate A, the period of the motion, B, the frequency of the motion, and C, the angular velocity of the motion, and D, total energy, and E, maximum velocity of the motion, and F, the maximum acceleration. Solution. M equal 30 grams, which is equal to 0.03 kg, converting it to kilogram. And amplitude A is equal to 0.6 meters, and the force constant K is equal to 0.8 Newton per meter. So the period is equal to 2 pi over omega, which is 2 pi root m over k, which is equal to 2 pi root 0.03 over 0.8 seconds. B, F equal to 1 over t, which is equal to 1 over the answer gotten earlier. C, omega is equal to 2 pi f, which is 2 pi times 1 over 2 pi root 0.0375 radians per second. When we simplify, your answer will be in radians per second. D, total energy E equals 1 over 2 Ka squared. That is 1 over 2 times 0.8 times 0.6 squared joules. E, maximum velocity Vm. Since half mv squared equals half Ka squared, by energy conversion, we have the Vm equal to root 0.8 times 0.6 squared over 0.03 meters per second. Or, since V is equal to omega A, we can simply say 2 pi f times 0.6 meter per second. E, maximum acceleration. This is equal to A equals minus omega squared A equals 2 pi f squared times 0.6 meters per second squared. Question 3. A simple pendulum is 50 centimeters long. Find its period. Solution. Take G as 10 meters per second squared. The period is equal to 2 pi over omega, which is equal to 2 pi root L over G, equals 2 pi root 0.5 over 10. Note the following. For a simple pendulum, the period T is equal to 2 pi over omega, equals 2 pi root L over G. While for a loaded spring, the period T is given as 2 pi over omega, equals 2 pi root M over K. So for a simple pendulum, we make use of L and G, while for a loaded spiral spring, we make use of M and K. Question 4. A body of mass 36 grams is placed on a spiral spring and it was pulled gently by means of a spring balance which records a frictional force of 100 Newton. If the spiral spring is turned by 0.4 cm, find the period of the motion. Solution. Using Hooke's law, F equals Ke, but M is equal to 36, which is equal to 0.036 kilogram. So 100 equals K times 0.4 over 100, converting our extension E to meters. So when simplified, our K equals to 2,500 Newton per meter. Hence, T equals 2 pi root M over K. That is 2 pi root 0.036 over 25,000. The answer is measured in seconds. That is the end of the topic, simple harmonic motion.